And our last speaker of this session will be Adam Kowalski from University of Colorado Boulder, and he will be talking about narrowband filter observations of stellar flares with Arctic and FlareCam. So Adam, take it away.
All right, great. Everybody, to answer Russet's question about Rachel's data, I discontinued that project when I saw the contamination, thinking it would get worse. And no, we didn't get any more data when this miracle occurred this past spring. So I'm going to talk about the project that I transitioned to, which is looking at the Bulmer jump in M-dwarf flares and high cadence monitoring with the Arctic. It's really exciting that there are now several groups in the Boulder area investigating M-dwarf flares, not even counting the solar flare cohort. These are my primary collaborators here. I just wanted to thank all the APOSS staff for all their work, which allows us to successfully execute these pretty complex flare campaigns, especially with the use of ArcSat and all the work behind the scenes making all this happen. All right, so I'm going to give a very quick visual introduction to solar and stellar flares to motivate high cadence monitoring and these two new filters that I bought for Arctic. And these two new filters I refer to as the 3500 and 4170 filters. And it's to build on work that we have done in the past with a different camera and a different telescope, well, several telescopes. This camera is UltraCam. I'm going to show some preliminary results from this new flare campaign, and then discuss future work involving comparable data of solar flares. And I just want to point out that if you're interested in using these new filters, please do. The performance details are linked there, including information on the red leak and count rates and all that. All right, so I'm going to introduce high time resolution flare phenomena with a movie of AUMIC and M-dwarf with a debris disk and a planet. And this movie spans 7 days, and it's part of a really exciting flare campaign from 2018, late 2018. It's going to show you data from the XMM Newton Observatory. The black light curve, the upper light curve, is going to be the X-rays. And you'll notice that it evolves very gradually during the flares. And then the bottom light curve is the near UV, what we think is mostly continuum around 2200 angstroms. And it's very impulsive, very spiky. All right, and so I'm just going to play this and maybe point out a few things to you as it plays. Okay, so here's a very large amplitude UV flare, small amplitude X-ray, and then you have the opposite occur with a very large amplitude X-ray, small amplitude UV. But generally, if you take the integral, cumulative integral of the UV, you get the X-ray curve more or less. This is called the Newport effect. I zoomed out here to show you the biggest flare in the sample and also the most impulsive. So we have a variety of phenomena to understand, and both of these light curves are at 10 seconds. And you can see that things evolve very quickly, especially if you're looking in the UV around 2200 angstroms here. All right, so I'm going to skip ahead now, and you can look at this movie when I link this here. You can look at the rest of the movie. Okay, so now I'm going to jump to the sun and show you the source phenomenology that we think gives rise to these two types of light curves. So here's an image from IRIS, and it's of a very famous, well-studied solar flare. You see the sunspots, the penumbra, the granulation, the spectrograph slit cutting right down the middle. I'm not showing the spectra here. I'm just showing you the really nice image here. And this is at 2830 angstroms, what we think is mostly continuum, kind of like the 2200 angstrom continuum that I showed for the stellar flare. All right, and so you see very compact, small, but very bright enhancements here. The brightest circular-like object, what we call a kernel, and the other diffuse structures are what we call ribbons. So this is a 2-ribbon flare, and this is very transient. It can be very bright for a very short time, and then it goes away. We think the origin of this UV continuum, which also has a connection to the optical continuum, comes from the bombardment of accelerated particles into the chromosphere, or deeper. And that those particles, which exhibit a power law distribution, emit hard X-ray Bremsstrahlung, shown as the black contours there. And we think that occurs very close to the solar surface. The material there explodes and ablates into the magnetic loops and shines brightly in the soft X-rays, shown here as the thermal contours, and these contours are from RESI. Okay, so this explains the time evolution from one wavelength to the other, from a very impulsive wavelength to a very gradual wavelength. Now I'm going to flip to the next image in this data set, just showing you the near UV continuum. All right, and I'm going to flip back and forth. Okay, you can see that there's some apparent motion of what we call the foot points, the kernels, the ribbons, and they spread apart from each other. And this is only 75 seconds later. So if you want to characterize the source properties in that bright kernel there, you better not integrate for too long, or you'll catch all this as well. And that will kind of mix into the signal. So if you want to map the properties in the very bright kernels in the very start of the flare, you need very high time resolution. Another really interesting thing is that if you take the intensity in that bright kernel there, and you divide by the flare intensity in the blue optical, that's what we call the Balmer jump ratio. All right, and hydrogen recombination in the chromosphere predicts a ratio of about 6. If you instead take the Balmer ratio as the ratio of the 3500 angstrom intensity, so closer to the Balmer limit, closer to the optical, divided by the blue optical intensity, the predicted recombination Balmer jump ratio is 10. Okay, so what's really interesting is that when we measure this ratio in M-dwarf flare spectra, we get ratios that are far from this value. We get ratios that are much smaller. This means that, at least according to our recent interpretation through radiative hydrodynamic models, that there are moderate to large optical depths in the continuum at 10,000 K in the deep atmosphere. And this is pretty remarkable. So here I show several spectra, all from DIS, by the way. There's the red flare spectrum here, is a very energetic flare in WASI-CMI, and it has a continuum in the optical that can be roughly represented as a 12,000 K black body. And then the spectrum that is blue colored is clearly different. It has a larger Balmer jump ratio of about 4, and not such strong evidence for this 10,000 K black body. For this flare, we also had a spectra from the Hubble Space Telescope out in the near UV, and I just show the wavelength of the iris bandpass for the solar flare in the previous slides here. Okay, so what we're going to do is we're going to measure the Balmer jump ratio statistically for a large number of flares at high time resolution to determine the occurrence of this type of flare spectrum versus this type of flare spectrum. And both of these are attained at the peak of their respective flares. So what we do is we measure the Balmer jump using 3 carefully selected narrowband continuum filters. So by selecting your continuum filters in a careful manner, you actually don't need full spectra to differentiate between these two types of events. And in particular, a strategy was devised by Suzanne Hawley and Mihalis Mathiadakis using a 3500 filter and a 4170 filter. And then you can take the ratio of the two and get a Balmer jump ratio. In the red, the ratio is 1.6, in the blue, it's 4. What's more interesting is that the type of flare spectrum you see at peak seems to be related to how fast the impulsive phase of the flare is, whether the impulsive phase has a high impulsiveness, what we call an impulsive event, or the impulsive phase has a low impulsiveness. It's more gradual. The third filter we're going to use here is on ArcSat, right here. Okay, so we have this nice picture emerge. We have impulsive flare events on the left. We have gradual flare events on the right. And we have flare events that resemble both of these, what we call hybrid or mixed flares. And the hybrid or mixed flares have periods of fast rise and also very pronounced slow decay. And all these light curves are at about the same time resolution and very similar stars. And we devise this impulsiveness index. We take the peak divided by the 4/2 max of the impulsive phase, and we get this impulsiveness. And I indicate that here, 16, 1.4, and 0.4. Of course, we don't think there's like discrete groupings of flares, but it's like a continuum, just like spectral types. We had this nice picture that emerged, that impulsive flare events had small Balmer jumps. Gradual flare events had large Balmer jumps, and hybrid or mixed flares had intermediate Balmer jumps. And that was from spectral observations for my PhD thesis. And then we got this high time resolution data set from Ultracam using these two filters, 3500 and 4170. And things got really complex. We generally saw this same pattern emerge when we had spectra to verify what we were saying with just these two filters. But we also saw some impulsive flare events that had, moderately sized Balmer jumps. There was another really interesting property of the impulsive flare events, is that some of them showed this really intriguing phenomenon of this 10,000 K black body continuum in the optical. This is really interesting because this is as far from a solar flare model prediction as you can get. This is as far from optically thin hydrogen recombination radiation as you can get. So a signature of this means that there are large optical depths in the continuum at 10,000 K in your flare atmosphere, which is really, really hard to do. And here's an Ultracam light curve in 4170 at 1.1 seconds, showing a remarkable flare, about 100 times more energetic than the largest solar flares. And then on the right axis is the color temperature using the 4170 and a 6,000 angstrom narrowband filter. And as Rachel mentioned, the temperature gets to about 10,000 degrees in the rise phase and peak, and then drops off very quickly in the decay phase. And then you have these really interesting variations to nearly 11,000 at the peak of this big one here. But when you bring the Balmer jump filter into it, the 3500 filter, the 10,000 K black body cannot explain that. So we need still some Balmer continuum emission to explain the full spectral energy distribution. So in comes the flare monitoring with Arctic. So what we do is we use a 3500 angstrom filter and a 4170 angstrom filter. These are designed by Asahi with updated UV transmission coatings. And to get very high time resolution, we just choose one of them, okay, because of the filter wheel rotation of Arctic. If we choose 3500, then we can measure a Balmer jump ratio of 3500 over 4750, where the 4750 is measured with ArcSat. And so we're running two telescopes at the same time to get a cadence of about 10 to 15 seconds. And we have some upcoming time in August to get simultaneous data with TESS. I already have a flare on CR draw with TESS, but I'm not going to show that here. Okay, so for the first night of observations, we observed YZCMI again, and we rotated between the two filters, 3500, 4170, 3500, 4170, and we got about a 1-minute cadence. And these data were analyzed by two undergrads in astronomy 3520 at CU, and showing the very nice flare events later in the night there. The 3500 is the blue and the 4170 is the green. And on the right is a zoom in of these two events and the calculated Balmer jump ratios. And they did a really nice job with this analysis, exploring the systematics that occur when taking a ratio of the emission in two filters, when the two filters are not observed at the same time. And so you can get an idea of the uncertainties due to time resolution here. And the Balmer jump ratios are relatively large, certainly much larger than a 10,000 K black body right here, shown as this dot dash line, and much larger than what we'd expect for an impulsive flare event. Okay, then I settled on a strategy using 3500 with Arctic and 4750 with flare cam to get much higher time resolution. And then on EVLAC, we got really lucky, had an amazing night. And here are the light curves. The 3500 is shown as black here in the right axis. Several events early on. This is typical for such a flare star, and then a big flare event towards the end. And it increases the flux in 3500 by about 7.5 times. And then the ArcSat 4750 filter shows some really interesting variations as well. We probably wouldn't believe these here unless we had the 3500 and the very high signal to noise data from the 3.5 meter. And then it shows about a 30% increase at the peak of the flare. I zoom in on the right side here to show you the flare at high time resolution. And so what you have here is a decently resolved rise phase, a fast decay phase, what we call a stalling phase in the fast decay, more fast decay, and then a beautiful exponential decay with a decay constant of 2 minutes. Okay, the 4/2 max of the light curve is 70 seconds. We divide that into the peak, and we get an impulsive index of 5. So this is an impulsive flare event. We take the Balmer jump ratio after we do a flux calibration, and we find this is a rather large Balmer jump, signifying that we have a bright Balmer continuum here for an impulsive flare, which is basically outside of the picture that I developed for my PhD. All right, and so this led me down a path of exploring some parameterized flare models at high time resolution. Here's that flare, and I've normalized the time axis by the 4/2 max following the analysis of Davenport et al. 2014. And the blue dashed curve is the double exponential decay parameterization from Davenport et al. 2014 using lower time resolution Kepler data in the optical. And that is cadence about 1 minute, of 1 minute exactly. And so you can see here, it does a really, really nice job with the overall trend in this relatively simple flare. This is much more simple flare than I've really seen at high time resolution. And so I wanted to investigate other possibilities here, including the rise phase, and I stumbled upon a fractal diffusive model from Schwanden. This is a model for area changes in solar flares, and that's shown as the red here. And it's highly fine-tuned, very preliminary work, just to show you that it seems to do okay. However, with these parameterizations, they rely on an exponential decay, sometimes two constants, and then there's even more parameters in the Schwanden model. The Schwanden model has no flare physics in it whatsoever. It's based off of Brownian motion statistics. So what we really need is forward modeling with actual flare physics that gives us some insight into these parameterizations in these types of models. Okay, so bringing everything together, we need forward modeling to model the Balmer jump ratio, that is the optical depth in the continuum at 10,000 Kelvin in the flare atmosphere. And we need forward modeling to tell us about the time scales of how that radiation from the flare chromosphere evolves. And to make progress on the second point here, we really need solar flares to tell us how the area changes, how the emission in one kernel rises quickly and then decays exponentially or in some other way. And there's this really unique data set from the Dunn Solar Telescope right next door with 3500 and 4170 filters with the ROSA instrument. And here I show high cadence movie that I'm going to loop. Hold on. Okay, and it's not as dramatic as you might be used to with solar flare movies, but you can see it right here occur over the sunspots. It's just looping over a few minutes here. Really interesting data set, and I think will help clarify some of these phenomena we see in the light curves of stellar flares, in particular, the impulsiveness index in the impulsive phase. Okay, so that's here are my conclusions. What we're doing with Arctic is we're basically allowing us to say, to establish relationships among the Balmer jump and the impulsiveness of a flare statistically, and to determine how they're related, if they are at all. This is really important because for tests, for example, many groups just take a 10,000 K black body and extrapolate to the UV. But with the Balmer jump measurement, we know that this is not correct, and maybe and is only correct in the impulsive phase of some impulsive events. And so this is really important for extrapolating optical broadband filters. Now I think we have enough data to say these oddballs that we saw at high time resolution with UltraCam are really interesting. That is the impulsive events with moderately large Balmer jumps. And what this means is that there's moderate optical depths in the continuum at 10,000 K, still very hard to produce with a standard solar flare heating model. And finally, I think we really need solar flare data that is comparable in the same filters, high time resolution, to understand the physical origin and impulsive type events and gradual type events.
Okay, thank you, Adam. So we only have time for one quick question before heading off to the break and then poster viewing. So Yuta, I'm sorry, you're just clapping. Okay, well, I think we should head off to the break, and we can then reconvene in the poster session in about 10 minutes.